Here we go again. Welcome to our Radar in Action online lecture series. My name is Jens Wieger and I'm glad you're all joining us again. Today we are talking about important tools for autonomous driving. There are still a great many challenges to solve before autonomous vehicles really do enter everyday operation. We all agree that a large number of different sensors will definitely have to be used on the vehicle. These definitely include radar sensors because of their daylight and weather independence. For development and testing, however, you need simulation data in, for example, radar data from realistic traffic scenarios, and that is not too easy. Nevertheless, my colleague Stefan Wald and Thomas Dahlmann have dared to tackle this task, and they will show you the results today in the presentation, Synthesis of Raw Data in Traffic Scenarios by Ray Tracing. Please, Thomas, go ahead.
Thank you very much, Jens. I will be your speaker today. I'm Thomas Dahlmann from the research group Aachen, and together with Stefan Wald, we did a lot of work on traffic simulation, both using software tools and hardware systems. And now I will talk a little bit about our simulation software Goprosim and how it can be used and how it actually can be connected to a different system called Atrium. And this is what I will present in the following. So let's first start by trying to understand what actually radar perceives from its environment. So we will not talk about how a radar processes data. Actually, we will more focus on what a radar sees. And let's just assume that we have a radar built into this vehicle here on the right, and it looks forward. And so what we can actually do is, if we have another object here, we can measure the distance to this object. We can measure the velocity the vehicle actually has, and we can measure under which direction it is located. So we can mostly determine the velocity of another object and the exact location. And an example for that you can see on this slide here. This is a measurement we did, which we recorded out of a moving vehicle, as you see here. So this is just a traffic scenario we have here. And here you see a so-called RangeDoppler map. This is a map you will see on the following slides several times. Down below here, we have the radial velocity, so the velocity of the cars and the objects in front of you. And here we have the range. And you have to consider that we are moving by ourselves, which means that if you're looking at a relative velocity, that means that everything around you is moving as well. Yeah. And so you see here some reflections. So these are these dots here in green and in red. And these are actually the reflections from the environment. These can be these delineators here. This can be here some of the ground or some of the bushes here or some of the vehicles. And we see that we are currently driving with a speed of 100 kilometers per hour. And we also see some reflections from other objects like this one here. So this is in relation to us driving at 20 kilometers per hour, which actually means that we have a certain difference in velocity to this vehicle, a difference of exactly 80 kilometers per hour. So you see, you can get a lot out of the data which is recorded by a radar, and now you can directly say, of course, well, that's great. We can use that for automated driving. We can realize automated driving functions with this. That is clear. But as soon as you get this idea, you can also start to directly ask some questions. And these are some of the challenges of autonomous driving. First of all, if you want to use such a sensor, this means that you have to rely on it, that you really have to make sure that it is not perceiving something in a wrong way or is detecting something in a faulty way. So you must be able to really avoid errors or making errors with the sensor. And that is something which is really hard. So if we are looking at level 5, which is full automation, so the vehicle does mostly everything by itself. It drives wherever you want by itself without you having to control the steering wheel or anything. This would actually require precision of one error per several million kilometers, so that you can be sure that this sensor works well with this requirement. Yeah? So from this directly comes a question that, well, if we want to do this, how can we test automotive radar sensors as comprehensively as possible to consider these many kilometers and make sure that no error occurs within this range of within this distance? On the other hand, you can see actually an example how such a vehicle looks like from an electromagnetic perspective at 77 gigahertz, where most automotive radar sensors work at. And you see that the car is not just a single reflection or a single blob. It's actually composed of a lot of reflections all around the vehicle. So it looks really like a top-down view of the vehicle. And that means if this vehicle is in front of you and it changes the track, for example, then you will illuminate different parts of the vehicle, which means that what is reflected back by the vehicle, the so-called radar signature, changes over time, over frequency, and over angle. So this means everything around you is much more complex than you might expect. And if you want to be able to test your radar sensor as well as possible, then you also have to test it as realistically as possible and consider this complexity here. So of course you can approach this using simulation methods. So you can go for numerical field computation, and there are mostly two different ways you can do this. You can use exact methods. These can be local methods based on solving some differential equations, or it can be done by solving integral equations. These are global methods, and perhaps you have even heard the names behind it: finite element and method of moments. The problem with these methods here is, since they are exact, they only work for objects which are a few wavelengths tall, and well, at 77 gigahertz we have a wavelength of 4 millimeters. So solving something with exact methods takes a huge amount of time, an unrealistic amount of time. So we have to go for asymptotic methods, which are either field-based or source-based. So these are geometrical optics solver or a physical optics solver, and these are much more performant for large-scale problems. Yeah, so we can go for these methods here if we want to tackle the problems in autonomous driving. And just to mention that very often some of these numerical field computation methods are so-called hybrid methods. That means that they are, for example, using both geometrical optics as well as physical optics. So let's go for one approach you could choose there. This is our simulation tool Farad, which is based on shooting and bouncing ray tracing technique. And what you can see here is that we calculated a RangeDoppler map for a scenario where you have here the transmitter and receiver, you have a bridge here, and you have two vehicles which are moving in different directions. And you can actually see that the objects are here, here, and here. But what you also see is a lot of distortion, a lot of artifacts. And the problem is that these artifacts are actually not from the environment itself. These are artifacts from the simulation. This has to do something with the properties of the shooting and bouncing ray tracing technique, which is based on stochastical processes. So that's something which can only be avoided if using more computational power and more computational time. The problem is, even for calculating this here, you have a computational expense of just having one of these RangeDoppler maps here getting calculated. That takes 1 day. Yeah, so that takes a long amount of time. And if you want to do even more time steps like 128, then this would require approximately 3 months. So this is really tedious and not the way we can go. So Farad is a great tool for other problems, but not such time dynamic events which you see here. So what we developed instead is our Goprosim software, and you see already that Goprosim stands for geometrical optics and physical optics, so it's a hybrid approach. And the geometrical optics part makes use of so-called time dynamic analytical ray tracing. Time dynamic means that you can simulate a dynamic scenario, so a scenario developing over time. And analytical means that we have a very specific ray tracing approach here, which actually restricts the number of reflections you can have within your scene, but instead boosts up the simulation in terms of computational performance a lot. Yeah. And so we can at least consider to a certain amount multipass propagation, although not to the same extent as shooting and bouncing rays. And this is based mostly on the assumption that we have mirror sources, so we can make use of reflection on surfaces. On the other hand, we have also physical simulation aspects in here, so we can solve the physical optics integral, which means that we can model scattering realistically. So each polygon here is scattering in a realistic fashion power. And we can also directly extract the Doppler shift, which is occurring at each polygon here. Coming back to the multipass propagation, what does mean we are restricted a bit? Well, you can see it here. So the direct reflection, of course, can be simulated, that's clear, but we can also simulate a bounce over another surface, like, for example, the ground for the transmit side, as well as for the receive side. And we can even simulate two bounces on another surface. That's a limit, but we studied this in very great detail and came to the conclusion that the accuracy of the simulation is still very high. So if you want to use this tool, how can you do it and which flexibility do you have? So let's have a look at how you can assemble a scenario. So we have here a database of different objects, and we can now start to assemble the scenario here. So for example, we can place these delineators here, we can place the body of the vehicle here, and we can place the wheels separately. And this has a very big advantage, which you will see later on. So what you can do here is actually you can move the whole vehicle, including the wheels, along a translational movement, but at the same time, you can add a rotational movement to the wheels. Yeah, and so this means that certain parts of the object you are moving around can have an additional motion. Yeah, and you can even go into more possibilities there. So here you see a human body model, and you can actually move the limbs of this model here separately. So you can add to the arms, for example, a rotation, which is happening on a sinusoidal basis, the same for the legs. And for the whole torso, you can, of course, add a linear constant movement, which is actually the movement forward. And additionally, you can add a sinusoidal movement along Z, Y, and X. Why should you add the sinusoidal movement here? That is something you can see here, and which you can also define in Goprosim. Normally, the body of a human moves in a very specific fashion. So, for example, it goes up and down in a vertical direction while moving forward. Additionally, the person moves from left to right while going forward. And you also have a so-called progressional shift, which means that you accelerate and decelerate while moving forward. So your torso goes a little bit forward and backward while moving forward in total. So this is the complexity in movement you can actually consider. And after you have modeled your environment, you can go into the simulation. And for the simulation results, you can actually choose between two different types here. The first one is the raw data type, which we will have a look at in the beginning. And after that, we will have a look at Arraylists, which are for a very specific purpose. But let's assume that you have raw data coming out of your simulation. And what we will now look at is a scenario which we simulated. And we will look at a RangeDoppler map, which was processed out of the raw data. So based on the raw data, we did a RangeDoppler map. And here you see what is actually happening. We are in this ego vehicle down here, and we are moving through this scenario where several vehicles are moving within. So some are approaching us on the other lane, some are on the same lane and are directly in front of us. And the first question you are able to answer if you look at this simulation here is the question I posed in the very beginning about the realism of the simulation. So if you look at the RangeDoppler map, you see just single dots. So you might think, well, the simulation is actually not taking that much realism into account. But if you look here at this single car down here, so here it is zoomed in, then you see these blue points here. These are the dominant scattering centers which were identified for this vehicle. And you see that actually the scattering centers are modeling the vehicle in a much more complex fashion. And you can even calculate the radar signature, which is perceived by the radar, which means that you just draw which reflections you get over time or over distance, and you see that there are several reflections occurring along the side of the car. So each vehicle is modeled by a multitude of scattering centers. Now we can go on and just see how this scenario develops. So we are now moving to a different lane. So we have some kind of maneuver, and you also see that this simulation is taking quite a long time, and you will see why this is important later on. So here you again see a certain static situation, and we will now look a little bit into more detail what you can actually see in the RangeDoppler map. So first of all, we have this vehicle here, which drives in front of us, which has approximately the same velocity of 10 meters per second at a distance of 25 meters. We have these poles here, these delineators, which are standing still. Of course, they are static, but since we are moving, they are moving with a relative speed of 20 meters per second towards us. We have this vehicle approaching us here. It itself has a certain velocity, so the total velocity is actually 30 meters per second, which means that this one here has a velocity of 10 meters per second. And we have even some more delineators at a larger distance. So you will not see them here on the right, but on the left, this is some kind of zoom out of the scene on the right, and you see that there are some more of these poles. So you see quite a complex and long scenario. If we look into the details, the scenario time was 17 seconds. We discretized this into 40 milliseconds time steps, so quite a lot of single time steps we simulated here, and we had in total 24 simulation objects. These were vehicles, these were was a road, these were these delineators, and so on. And for each, there is a CAD model which is included in the simulation. And the simulation time in total was 22 seconds. So we are very close to real-time operation here. A very fast simulation for such a complex electromagnetic simulation. We can even compare this again. So if we compare it to our Farad simulation, then you see that here the simulation time per time step took around 1 day. And if you calculate the same for Goprosim, then you see that the simulation time per time step is only 0.12 seconds. So again, you might say, well, but if you look at these targets here, they are not really complex and there is not that much going on. But actually, we can zoom in here and see some fascinating details about the simulation. So I already told you that the vehicle, the wheels are moving separately, and these has some certain effects which we call MicroDoppler effects. So this separate movement actually causes something in the RangeDoppler map. So this is a zoom in of this Doppler map, RangeDoppler map, and we see that the vehicle itself is moving at 10 meters per second, but we have orthogonal to this line here, which represents the body of the vehicle, we have these lines here, and they reach from 0 meters per second to 20 meters per second. And these are actually the wheels. That's the interesting part about it. So we can actually see that, for example, the point touching the ground, this point at the wheel is moving backwards in the backward direction. So it actually has a velocity of 0 meters per second, whereas a point which is located on top of the wheel is moving towards the radar and therefore has double the speed, so 20 meters per second. So this is actually an effect coming from the wheels, and this can be very interesting for analyzing and can be also very interesting for certain signal processing algorithms for automotive radars. You can also, for example, choose a different way of visualizing that. So this is just a Doppler along time step, and you also see this Doppler spectrum here reaching from 0 to 20 meters per second. We can even do some other processing here. So we can, for example, rotate the vehicle around a certain range, angular range. And you see by doing this and mostly just doing, in addition, a RangeDoppler processing or creating a RangeDoppler map, you can even, as you see here, plot some kind of visualization of the vehicle where you actually see, again, a top-down view of the vehicle. And you can identify now where the reflections actually occur. So, for example, at the trunk of the vehicle. And here is the windshield. There you also get some reflections. Here are the side mirrors. So you can actually recognize certain details. By this, you can analyze how such vehicles respond to electromagnetic wave and which parts of the reflection are the most prominent. And this was recorded for the vehicle facing upwards, and this was recorded for the vehicle facing downwards. So you see that the illumination direction is different in these two plots here. So a lot you can do with these simulations and a lot you can get out there to actually test your signal processing algorithms. But I already mentioned that there is something else you can do, and this is generating Arraylists. And this is directly connected to our radar targets. First of all, what is a Arraylist? Arraylist contains for each time step a certain amount of information, and this information is now shown here. So this is the scenario we are simulating. Here is the radar, here is the approaching vehicle. And of course, if we are actually sending out a wave, then this wave gets reflected here. And by this, we have amplitude and phase of the wave, which is arriving at our receiver. This is what these two values are given within this Arraylist. Then additionally, the array, of course, is reflected at the vehicle and therefore delayed by a certain amount of time. And this happens under a certain angle, which means that we also include in the Arraylist the azimuth angle and the delay. And of course, both vehicles have a Doppler shift, and therefore we are also including the Doppler shift into the simulation. So what to do with this information? In a connected project, we developed our Atrium radar target simulator, and this is actually a system which is shown here. This is a hardware which allows for over-the-air verification of radar sensors, and this means that you can just place a radar sensor in front of this target simulator, and it will actually generate a virtual environment. And it can do this for multiple radar targets, also for complex radar signatures. It will do it along range and angle, and of course Doppler, and is built and meant for the simulation of critical complex traffic scenarios. Yeah, so that is actually the intention of the system. And so you already see that it's very closely connected to the system we have. So just to understand how this works, so the automotive radar here sends out some signal which is received, and this can be delayed by a certain amount of time to simulate distance. You can change the Doppler, so to simulate a certain velocity. You can change the magnitude to simulate a certain reflectiveness, so a certain brightness of your echo. You can change the phase, and you do not only do this once, but you do it several times so that you can simulate several reflections, and you do not send it along one direction, but several directions so that you actually can also simulate an azimuth angle. Our system is a little bit more complex, so we additionally do a certain signal analysis, then we put this onto a synthesizer, and since we want to save bandwidth, since this allows us to generate more echoes, we just generate here signals with a small bandwidth and stretch them up with additional transmitters. And by this, we can then do a very complex radar target simulation. And of course, this is completely interwoven with the Goprosim simulation software. So that is something you can see here. You would normally progress with the software as or with the system as follows. You generate a traffic scenario, then you generate Arraylists using Goprosim, then you do some post-processing, and then you load this information into the radar target simulator to simulate the traffic scenario. There are certain configurations given for the Atrium system. So this here is the first generation, which can simulate up to 16 echoes. So here we put together a RangeDoppler map in the shape of an A for Atrium. but the second and third generation can do even more, since this is only capable of 16 echoes at a bandwidth of 1 gigahertz. Our new generation can simulate up to 4 gigahertz and can generate up to 384 echoes for 96 directions, so 96 channels. And here you see two RangeDoppler maps, one with 80 echoes and one with 122 echoes. So that's it from my side. That is my presentation. So what I introduced to you is the physical radar simulator Goprosim, which allows for a time discrete simulation and can either output raw data for testing signal processing approaches of radar systems, of automotive radar systems, or can output Arraylists for our radar target simulator Atrium to do a hardware over-the-air simulation. And here you see the whole spectrum of the software, reaching from ISAR imaging over MicroDoppler generation, complex radar signatures, up to over-the-air simulation with Atrium. Thank you very much for your attention, and I would be happy to receive your questions.
Thanks for the interesting presentation. Challenging, but good to follow. I hope you all were also able to follow along well too. In any case, there are already a few questions as well. Are there any requirements on the vehicle mesh size relative to the wavelength of the radar?
There is, of course, a connection. The point here is that you have some kind of proportionality. The more polygons you actually include, the better you converge to, for example, shooting and bouncing ray technique, or the more exact the solution is. So of course, that will make an effect, but still, due to the simulation principle, we are still a lot faster. So that is for sure, and that is an advantage. However, it really depends on what you want to simulate. If this environment is very complex, then increasing the accuracy there is perhaps not even required, because you will never be able to simulate it with that many details compared to a realistic and to a real environment. So the agreement is still sufficient. Also, if we are doing a hill simulation with the Atrium system, then due to the reduced complexity which is allowed by radar target simulation, we also do not need to get that high. And so normally you can go for less polygons and can adjust this depending on what you actually require in your simulation.
Yeah, thanks, Thomas. What material parameters are used in the simulation? Are the material parameters measured?
Regarding material, we in most cases are currently just assuming PEC, perfect electric conductors, which is mostly due to the fact that at these high frequencies, most surfaces act like just perfectly reflective surfaces. So this assumption is in most cases valid. And before you say, well, I think that must not be the case, we checked it. Of course, we checked that, and we performed comparison simulations to make sure that we are as accurate as possible compared, for example, to our Farad simulations or other method of moment approaches. So we can actually agree that this is fine what we get out of the simulator here.
Here's the next question. Did you perform a side-by-side comparison of simulated versus measured radar return? If so, can you highlight the features that are accurately and less accurately represented?
Yeah, I can say something about this. perfect question, actually, since it's really connected to my last answer. Yeah, we did a side-by-side comparison of especially simulated results. So we compared method of moments with shooting and bouncing rays with analytical ray tracing, and saw a great agreement between those simulations. For that, we used actually the calculation of the radar cross-section over angle. So we mostly recorded the RCS or simulated the RCS of a vehicle from different perspectives. Of course, the agreements are less good for orientations where you get a low amount of reflections. Yeah, so there you normally have disagreements, but especially for the front and the sides, you get a very good agreement. So this is sufficient for comparison with real measurements. Of course, you are always a little bit limited there, but we also did this for dynamic situations. So we had some scenarios which we where we did some recordings with a real. We did them on a test track. We measured this situation and compared if Doppler and range and the scatterers we can see within this environment are agreeing in the Goprosim simulation and the actual measurement. So these were the comparisons we did, and where we saw a good agreement. And as I said, the where we have a worse agreement is actually where we also get less reflections.
Okay, here's the question: how stable is the system against artificial disruptors, for example, jammers, or can they be eliminated by an algorithm? Yeah, can you say something about this?
Yeah, sure. So, I mean, this is a virtual environment. This is a simulator. So we do not really have jammers in there or any need for some interference mitigation. Of course, this is an important topic for automotive radars, and this is something which can be investigated as well with our system in principle. However, it is not really something which we have to avoid all the time. It's just we have a simulation suite here which we can use for different purposes to validate radar sensors, and so we can use it for any scenario you can imagine, or most scenarios you can imagine, and so you not always need to avoid any jamming or something like this.
Okay, now why is the frequency of 77 gigahertz is chosen for this radar?
I assume that this question goes more into the direction of why automotive radars are using this frequency and not why we are using this frequency in our simulation. I will nevertheless try to answer both. So for radars, there are actually two reasons. The first reason is the higher you go in frequency, the more bandwidth you normally have available, and bandwidth means that you can resolve objects to a finer degree, and that means also that your system gets smaller, so you get some advantages from choosing higher frequencies. The other reason is that you actually need to find frequency ranges or spots within your frequency spectrum which are available to do this. And so there was a lot of effort put into agreeing that this frequency band reaching from 76 gigahertz to 81 gigahertz is actually worldwide available for automotive radars. This is an agreement which was done by a lot of authorities and after a lot of discussion and agreements. And so the automotive manufacturers, especially the sensor manufacturers, are now very happy that they have this frequency range available for automotive radar. So this is the main reason why this was chosen. From simulation perspective, I can actually say for us, it does not really matter as long as the objects we are simulating are much, much larger than the wavelengths, which is at least at 77 gigahertz for vehicles the case. So using Goprosim is not restricted, of course, to 76 to 81 gigahertz, but is available for any frequency. But we cannot simulate or get good results if the objects are in the same the size of the object is in the same range as the wavelengths, which would be, for example, at 77 gigahertz, 4 millimeters. So if you have 4 millimeters objects, they cannot be simulated that well.
No, thank you. Yeah, can the atrium also do road reflections and elevations?
Yeah, so it can actually do road reflections. The reason for it is very simple. Goprosim can do it, and Atrium just simulates or emulates what it gets as dominant reflections from Goprosim. So since the road can be a reflective surface, you will also be able to pick up reflections from the road surface. For the elevation, it really depends on the configuration you choose for the antennas. Of course, if you we have a limited amount of channels, and if you arrange the system in a way that your antennas also allow to cover elevation, then you can do this. From a software side, it's possible nevertheless. However, this will again or directly affect your azimuthal coverage. So you will lose some channels for resolving the elevation.
Okay, thank you, Thomas. Which type of material properties of target surfaces can be modeled in the simulator, and how do you describe the material properties of the object?
I think that is something we already answered, right? Since we are mostly assuming perfectly reflective surfaces, and I also explained why this is a valid assumption. So I think we can actually skip this. I hope that it was understandable what I explained there.
Okay, good. Yeah. What are the advantages of multipass propagation?
Well, I would not say that there are advantages, but that's just what happens in the environment. So you can just have multipass propagation, since your wave can get reflected at the street and then get reflected at the vehicle and then get reflected at the next vehicle and then again at the street. So you see, in principle, you can have an infinite amount of multipass reflections. Yeah. So the question is more in the direction of, are you able to simulate multipass? And that is what I described in the very beginning. So we are able to simulate multipass, but only to a restricted amount. Of course, speeding up the simulation comes with a price, but as I already mentioned, the accuracy of our simulation is well enough that this assumption holds. And we at least can consider 3 bounces, which means that we get one reflection, then the next reflection, then the next reflection, and then receive the wave, which is already quite a complex happening. And that means that we are considering this to a sufficient degree.
Thank you. So we are very late. So here's the last question for today. Is there a way to add some modulation, different slopes and starting times, for example?
Yes, that's possible. There we have the complete freedom to choose this. We can add there any parameter or use any parameter which is possible and include this in our simulation. So this is actually doable. Yeah. Actually, perhaps this is also quite interesting. Currently, we are working on a system which will allow to do even a real-time simulation. So you saw that we are very close. 22 seconds was 17 seconds, so we are very close to real time. And what we actually can do here is with this real-time simulator that these parameters and positions are directly given to the simulator. The simulation is then performed in real time and is given back. So we can even adapt to it real time.
That's all the questions for today. Thank you again for your participation and the many questions. I hope you enjoyed our talk. Again, you will get a short survey tomorrow. We would appreciate if you would take the 2 minutes to answer the 4 questions. On Friday, we will also receive the presentation slides from today. And in case you didn't already know, and if you want to share the presents for your colleague and friends, 3 weeks from today, it will be published on our YouTube channel, Fraunhofer FHR. Finally, let's take a look at the next lectures. The next talk is on March 29 on scattering identification in ISA images with my colleague Simon Wagner. So if you haven't registered yet, do it now. See you in 2 weeks. Goodbye.